Hello, this is the fifth video for Graphs and Networks Series 3 on Further Graph Theory for OCR Discrete Further Mathematics, and it looks at Karatalski's theorem. Karatalski was a Polish mathematician, and his theorem is often used to prove that a graph is non-planar. It uses the K5 and K33 graphs that we met in the previous video. And to understand the theorem, we need to understand something called subdivision of graphs. If we take an edge in a graph and insert a new vertex of degree 2 into that edge, we are making a subdivision of the graph. So a new vertex between B and D, or we could also add a new vertex between C and D. So we can do this more than once, and each new graph formed is a subdivision of the original graph. Subdivision can be done in a number of ways. It is easy to see that creating a subdivision cannot change the graph from planar to non-planar, as no crossed arcs are added. Any subdivision of G is planar if and only if G is planar, hence subdivision preserves planarity. Note that G is a subdivision of itself. Remembering that we have already shown in a previous video that neither K5 nor K33 are planar. Karatalski's theorem states that if a graph contains a subgraph that is a subdivision of either K5 or K33, then it is not planar. Note this theorem gives a necessary and sufficient condition. So, for subdivisions of K5, we look out for the pentagon star formation on a subgraph that has 5 nodes of order 4. For K33, we look for a subgraph with 6 nodes of order 3 that are connected either in the bipartite version, or remembering that we can create the isomorphic version where we have alternate first and second set nodes, as shown here. K5 and K33 have other isomorphic forms as well, which you may wish to investigate for yourselves using GeoGebra or otherwise, so you can recognize them easily within a graph. You may need to look for a subgraph. So in this first left-hand side example, we can see that if we leave out this node F and its edges, then we have K5. In the middle example, you may spot that F is a vertex between A and E. So the graph is itself a subdivision. If we leave out arc FC, so in other words this arc here, then we form a subgraph, then we have the same subdivision of K5. So thus we may need to look for a subgraph that is a subdivision. So let's try and apply Karatalski's theorem and say which of these two graphs is planar. If we look at the first graph, there are 6 nodes, so that would indicate that we should look for K33. If we left out A, B and D, F, so in other words that line there and that one there, then we can see that we'd be left with 6 nodes of order 3. And therefore K33 is a subgraph. Karatalski's theorem applies and the graph is non-planar. In this second example, we again have 6 nodes. However, C is only order 2. and therefore we can see that K33 cannot be a subgraph. Let's check for K5. If we take out C and its two edges, then we would only have 5 nodes. And let's check their orders. Well, A and E only have order 3, and therefore it's not K5 either. Hence Kerates' theorem does not apply, and it would seem that the graph is planar. Indeed, if we were to move F and C, then we would take out this crossing and this crossing and this crossing. And then we would only then have to move E to remove the final crossing. And we could redraw the graph in this way, clearly showing that it is indeed planar. Contraction of graphs is an important concept in higher level graph theory, and it is when two vertices are pushed together into one so that any edge that is incident with the original two vertices is incident with the new contracted vertex. If two nodes A and B are contracted, we use bracket AB as the notation for the new vertex. Using this notation, in the example below, we can see that E and D have been contracted to become DE. Note that the edges DE and DB are in effect lost in that contraction. We could think of this process as the reverse of subdivision. However, graphs may also be contracted in many more ways. After a contraction, the new graph is referred to as a minor of the original graph. The Peterson graph is an interesting example to look at. You note that it has 10 nodes, and contracting the outer 5 vertices onto the inner 5, in other words, this vertice contracted onto this one and so on around the pentagon shape, leads to K5. The Peterson graph also contains a subgraph, which is a subdivision of K33. Now this shows that the Peterson graph is non-planar using Kerates' theorem. We can show this more clearly using this GeoGebra file. So the Peterson graph, if I look at contracting it to K5, note that those outer nodes are contracting in to their inner counterparts, and thus we have K5. With the K3, we can initially delete the vertices and edges, and then by contracting the nodes as shown, that's 3 nodes contracting down, and rearranging, we reach the typical K33 shape that we recognize easily. In the next video, we will look at the thickness of a graph.